Welcome back to Calculus 1. In this lecture, we're going to introduce one of the fundamental quantities in calculus called the derivative. We've been talking about limits. In this lecture, we'll give the limit definition of the derivative. All right, now if it's been a while, you might want to go back and rewatch our first lecture on the short Introduction to Calculus, just to focus on a single problem, and there's a whole bunch that we could start with. I like to focus on the tangent line problem. It's a very quick way to go from algebra. Think slope of a line, y2 minus y1 divided by x2 minus x1. And the tangent line problem very quickly brings us to the fundamental ideas of calculus. So we'll be able to answer that now that we've put the time in to understand limits. Okay, so the basic idea is here we have a graph of a function. We have the red tangent line sketched. And what we try to do is start by finding an approximate answer. Algebra requires 2 points. Here, the tangent line, it looks like it only passes through 1 point. So we introduce 2 points, a distance h apart, and we first start by finding the slope of the secant line sketched in black there. All right, and that's something that requires only algebra. The slope of the secant line passing through the 2 points a comma f of a and a plus h comma f of a plus h, that's really just your basic slope formula. The quantity you get after that is called the difference quotient. That might look familiar from your pre-calculus course, but this only requires the ideas of algebra. The conceptual leap occurs when we try to go from the secant line to relate that to the tangent line. So what we try to do, going back to the introduction to calculus, that lecture, we do something to make the secant line approach the tangent line. And what we do is we let the second point get closer to the first. We can do that by letting the distance h between those two x coordinates get smaller towards 0. As h approaches 0, this is the concept of a limit as h approaches 0. So basically here, now that we understand limits, we can state and solve problems now for finding the slope of a tangent line. It's pretty much the slope of the secant line, just with the extra step of evaluating a limit as h goes to 0. And this is something that requires the tools of calculus. We have this definition here of the slope of the tangent line in terms of a limit. Okay, and as it turns out, this is a central concept to all of calculus and mathematics in general. So let's go ahead and make this a little more formal, since this is kind of important. This is called the derivative of f at a, f being a function. A is the x coordinate at which we find the tangent line. And this quantity represents the slope of the tangent line. We're going to call that from now on the derivative of that function at a, where a is our x coordinate, a number. Okay, so let's give a precise definition here. This is what we're going to call the limit definition of the derivative of f at a. It's a mouthful, but we'll just be calling this the definition for the derivative of f at a. And it's pretty much what we arrived at by answering the tangent line problem through our introduction to calculus. All right, now that we understand limits, we can now evaluate this limit definition. Now, I want to point out this quantity that we're calling the derivative of f at a, which we kind of read as f prime of a. The prime notation is just one of several ways to denote derivatives, which we'll slowly introduce over the next few lectures. And we have to be careful here because we have encountered some limits that do not exist. So notice there in that definition of the derivative of f at a, we have in parentheses, provided this limit exists. So keep in mind, some limits don't exist. It might be possible for a derivative of a function at a certain x value to not exist, but that's going to be saved for a kind of a following lecture. Okay, so before we move on and take a look at some examples on being able to solve a tangent line problem, the derivative gives us the slope of that tangent line. Just keep this in mind, this quantity f prime of a, what we're calling the derivative, this represents the slope of the tangent line. And this is one of several possible ways to give an interpretation to what we're calling the derivative. At the end of the second part of this lecture, we'll give a summary answering the question, what is a derivative? We have one answer here. A derivative is a slope of a tangent line. All right, and with that out of the way, let's get to some examples. Since we're interested in solving the tangent line problem, we were mentioning trying to get the equation of the tangent line. We can now do that. Most of the work is in getting the slope using the limit definition above. F prime of a only represents the slope of the tangent line. We might also want the equation. But that's actually going to be really easy because it's just relying on familiar point-slope form from algebra. We have a point with coordinates a, comma f of a, and we have the slope now, which we don't calculate as rise over run. In calculus, we calculate the slope of a tangent line with this fundamental quantity called a derivative. Symbolically, we don't write that as m anymore, like we would have previously in algebra for slope. We denote the slope of the tangent line by f prime of a, what we call a derivative. All right. Notice there's a lot of different ideas, slope of a tangent line, notation f prime of a, what we're calling the derivative of f at a. They're all related and kind of mean the same thing. All right, with that out of the way, let's get to a kind of a preview or maybe review of a problem. Think back to your pre-calculus course. If you can, this was probably very early on. You had examples where you were simplifying this thing called the difference quotient. Now, we could have jumped straight to an example, but this is one of those kind of places where your algebra, really kind of algebra and pre-calc all thrown together here, either allows the student to be successful with our current problems in Calc 1, or the student's algebra and pre-calc skills might be a little lacking. All right, so let's just briefly go through an overview of how to simplify this thing called the difference quotient. F of a plus h minus f of a, all divided by h. All right, now there's a few steps which you might recall. We kind of break this down into first simplifying f of a plus h. So we're plugging in as input a plus h to our function. Then we simplify the full numerator. We're going to simplify f of a plus h minus f of a. And then once we've simplified that thoroughly, we then basically divide by h. Or equivalently, when you divide by a number, it's equivalent to multiply by the reciprocal. Sometimes it's beneficial to divide by h. Other times when dealing with fractions, it might be better to multiply by 1 over h. All right, now again, this is all a combination of algebra and pre-calculus. There is no calculus here other than recognizing this quantity represents the slope of the secant line. This is where probably 95% of the work in one of our problems lies, in basically going through these steps. I want to give you a kind of a realistic sense of how well you understand these ideas. Here's an example, again, typical for a pre-calculus course. Here's a function, f of x equals x squared minus 2x plus 3. Pause the video and give yourself an attempt at simplifying the difference quotient above for this function. We'll check in 1 or 2 minutes, maybe longer if you need more time, but you'll quickly find either you recall this topic from pre-calculus and you get it, or you're likely going to be stuck. in our course. Give yourself maybe a few minutes and we'll check in. Okay, let's go through this. Just how well do you understand all this pre-stuff, algebra and pre-calculus, all the stuff prior to calculus? Let's find out. Probably the biggest tip and source of errors is misunderstanding function notation. So here's a useful tip that I've used in my pre-calculus courses when I've taught them, which students tend to find to be helpful. Replace all x's in the function with parentheses. Keep in mind what x represents. It's your input, a placeholder for whatever number you plug in. Now, if you rewrite your function kind of above there, without x's, you have kind of f of something equals something squared minus 2 times that something plus 3. What we have to recognize is now, when we're plugging in a plus h, we have to plug that in every place there was an x. Or here, with this tip, we're going to plug a plus h into every spot in which there are parentheses or open parentheses. All right, if mistakes are made, it's likely right within this first step of simplifying f of a plus h. Hopefully you kind of got through that. If not, you got stuck and that was confusing, that's a great topic to reach out to me or your other professor about to make sure you can understand our current Calc 1 topics. All right, so we'll plug in a plus h and then simplify that. So FOIL, expand the first term, and then distribute that -2. All right, notice here there's no like terms, same variables to same powers, and just a collection of a bunch of different stuff, none of which cancels yet. Most of cancellation and simplifying occurs in step 2. We now subtract the two values f of a plus h, and we subtract from that f of a. Now, if you feel comfortable with your algebra, you probably won't make the mistake of forgetting here we have to subtract that whole quantity. So notice I used brackets there in red. So another useful tip, use parentheses, specifically around any quantities that you're subtracting. All right, so if you put parentheses here, red brackets, around f of a, that's basically kind of the original function just with a instead of x inside of it. We find here that kind of distributing that negative through the brackets, now there's a lot of terms that cancel. Everything left is going to have a factor of h in it. Notice here our surviving terms are 2ah plus h squared minus 2h. So that's what we'll call the consistency check, useful just for kind of checking simple problems throughout this kind of lecture on defining the derivative with the limit definition. And the check is that after this second step, most examples have all terms at the end of step 2 containing h. So once you calculate this difference and simplify it, all surviving terms should have a factor of h in them. So this quantity does. Everything has at least one power or factor of h in it. Now, why is that helpful? Think about step 3. We then divide by h. To make the connection to calculus, we saw indeterminate forms not too long ago. Why we want every term to have a factor of h in it, the consistency check, is so that way when we divide by h, we cancel the indeterminate form. So if we divide by h, we get this end result 2a plus h minus 2. And that's, for this pre-calculus question, a fully simplified difference quotient. Now, before we get to our real first example, this is likely where errors are going to occur in kind of simplifying this. The only remaining step now for us in calculus is to take a limit as h goes to 0. All right, let's get to our first example. This is a good one. We have a function here, f of x, given as x squared plus 1. And let's find f prime of 1. So let's calculate the derivative of this function at x equals 1. Now, keep in mind what we briefly reviewed, it might not have sunk in yet. A derivative, f prime of 1 here, represents the slope of a tangent line. We're going to relate that to part B, where we're asked to find the equation of the tangent line to this graph at the point 1, 2. Notice why it's 1, 2. If you plug x equals 1 into your function, 1 squared plus 1 becomes 2. So that gives us the ordered pair on the graph, 1, 2. All right, this is our first example going through this. I want to go through this with you together. If you feel really comfortable, you can certainly pause, but I would go through this first example with my course face-to-face. So let's do that together. Let's try to get a graphical interpretation just to get some idea of what our calculations should match up with. So here I start with the graph of the function, y equals x squared plus 1, a basic parabola shifted up 1 unit. And if we look at the point on that graph, 1, 2, and draw its tangent line, we have this kind of rather nice sketch. I took my time with that. That's arguably the best parabola that I ever sketched, just for you. Top notch. All right, and then this graph, as it turns out, when we finish this problem, we'll be able to kind of fully dive into what the tangent line is graphically. All right, now what I want you to kind of extract from this graph, or this graphical representation, is our tangent line sketched in red there. That tangent line has positive slope. So what we should find is that the slope of this tangent line, which we now call a derivative, the derivative of f at 1, f prime of 1 should be a positive number. Now let's see if we can confirm that with a calculation. As of right now, our only tool for calculating derivatives is the limit definition. Now, some of you might know some shortcuts, rules for calculating derivatives. We haven't arrived at them yet. The limit definition, as we briefly introduced, is what we use to prove those other rules, which we'll be getting to shortly. So let's make sure we can implement the limit definition of the derivative of f at a before we move on to some of those other shortcuts later in the course. All right, so we're going to use as our function f of x equals x squared plus 1. And since the question is asking us to find f prime of 1, the value for a, referenced in the definition earlier, will be 1. A is just the placeholder for the x-coordinate of where we're finding the tangent line. All right, so we're just replacing that in the limit definition. F prime of 1 equals the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. All right, and we just have to simplify this. Pretty much all of our algebraic tricks will apply. Think back earlier when we discussed the limit laws and limits with indeterminate forms, of which this would be. We'll give a follow-up on that in a few minutes. We had a few algebraic tricks, factoring, expanding, using the conjugate when the function has square roots in it, and then using a common denominator when we're adding or subtracting, working with several fractions. Well, take a look at your function here, x squared plus 1. When you plug 1 plus h into that, the only thing you can really do is expand it, multiply it out, and that's our algebraic trick here. So there's some work off to the side there, off to the right. That's our first step, plugging in 1 plus h. Make sure you're comfortable with that. A prepared calculus student should be able to get through that rather quickly. All right, and we just basically plug that in. Notice we have minus f of 1. F of 1 is 2. So we have f of 1 plus h, which is 2 plus 2h plus h squared. And then we subtract f of 1 from that, which is 2. All right, you can see here we can slowly start to simplify that. The 2's within the numerator cancel out. And while we still have an indeterminate form here, we can't plug in or evaluate this at h equals 0. There's an indeterminate form of type 0 over 0. We can factor h out and cancel it. If you do so, you're left with 2 plus h. And there we can evaluate the limit as h goes to 0, basically by plugging in h equals 0. We have an equivalent expression now, or function, with no more indeterminate form. So we get this limit evaluates to 2. What does this limit represent? This limit definition? It's the limit definition for the derivative. And that derivative represents the slope of the tangent line at x equals 1. Now, does that match with what we expected graphically above? It does. We expected to get a positive slope for our tangent line, and we find here that calculating this with the limit definition, f prime of 1 equals 2, which is positive, which is what we wanted. All right, so that pretty much does it for part A. We can now say f prime of 1 equals 2. More importantly, 2 is the slope of our tangent line. Now, with all that work done, we can easily answer part B. We have a point given, an x comma y, 1 comma 2, and we just calculated the slope, 2. So we're pretty much done. Let's put that work on the next page. Our point is given. Our slope, we calculated it with the limit definition of the derivative. We found that to be 2, and all the work is done. We just have to plug that into point slope form of a line. And if you plug that in, we get this. The equation of our tangent line here to the graph of that function, f of x equals x squared plus 1 at the point 1 comma 2 in the graph. Here's its equation, y minus 2, 2 being the y coordinate, equals 2, which is the slope, times x minus 1, 1 being the x coordinate. And that's it. Almost all the work is in applying the limit definition within part A. All right, now this can be simplified. This is kind of a correct full credit answer that I'd be looking for, but it's not the only form for a line. If you simplify that and solve for y, we get a simpler form, y equals 2x. So both of those are completely valid. The two versions here are the equation for the line written in point slope form, and then y equals 2x, y equals mx plus b form, that's slope intercept form. Both are completely valid and full credit. Okay, so that does it for example 1. If you were at all a little bit lost or weren't quite certain what we were doing, go back and rewatch our lecture on the introduction to calculus, but probably more importantly, our lecture on the limit laws when we were covering all of the different algebraic tricks for indeterminate forms of type 0 over 0. Okay, now let's tie this into the graph that we sketched. We just found our tangent line had equation y equals 2x. Now, does that match what we visually see here? Well, y equals mx plus b form, 2 is the slope, which if you take a look at that, it actually looks very accurately like a line, apply, rise over run, start at the origin. It looks like we go up 2 units and then over 1 to go from 0, 0 to the point 1, 2. So the slope seems to match the graph here, which the graph, I made sure to take care, was sketched accurately. Now what's even more interesting is the tangent line here does seem to pass through the origin notice the equation for that tangent line, y equals 2x. There's no b after x. The y-intercept is 0, which this graph confirms. So it's kind of nice how this all fits together. Graphically, if you sketch this in as much detail as I did, you might have expected the slope to be 2 and the y-intercept to be 0 for your tangent line. Most other functions, though, that's naturally not going to be efficient. The graphs are going to be sufficiently complicated, so we could only really just estimate from our graph if the slope of the tangent line is positive or negative. But for this simple function, I wanted to make sure we had that connection. Okay, now with that first example out of the way, let's kind of just give an overview. First, for what we're calling the limit definition of f prime of a, there's actually two versions for the limit definition. The one stated here is what we introduced within the introduction to calculus, and we just applied it in example 1. It's the limit as h approaches 0 version. And this works, but sometimes it's good to have more tools in your toolbox. So we're going to have an alternate version, which is equivalent. It's just basically different notation, but still the same concept. Calculate slope of the secant line, and then take a limit. And this is the other standard version, the alternate limit definition for f prime of a. And here our ordered pairs are a comma f of a, but x comma f of x. In order to make the connection, we don't evaluate a limit as h goes to 0. We evaluate a limit as the second x coordinate, x, approaches the first x coordinate, a. And that makes the second point get closer to the first. Same ideas and concepts, just alternate notation. Believe it or not, notation is one of the biggest things that tends to confuse students in the calculus sequence. All right, so these two definitions are equivalent. We'll look at some examples within part 2 applying each or both. Both will work. You might want to go through some homework questions to get a sense for which you might find to be easier. Again, that all depends on your background in algebra. All right, there's a second important thing I want to point out, just to give you some idea of how the course progresses in a standard Calculus 1 course. These two limit definitions always give an indeterminate form of type 0 over 0. Make sure you see that for each limit definition above. The first, we plug in h equals 0, and we get 0 over 0. The second version, we plug in x equals a, but we still get 0 over 0. No matter which version you use for the limit definition, it will always result in an indeterminate form of type 0 over 0. Now, while that's kind of, maybe not the greatest of news, since there was a lot of work in those indeterminate form questions, this is actually really good. The typical functions we'll be encountering at the kind of this point in the calculus sequence really only rely upon these 4 standard algebraic tricks that we introduced in our lecture on the limit laws. So when we get an indeterminate form, that basically is our clue to try an algebraic trick. So through all the examples that we'll be getting through within part 2, we just have to apply one of our 4 algebraic tricks. Either factor, expand, use the conjugate. The clue is when you have square roots, you'll probably use the conjugate. And perhaps to use a common denominator. Now, what we get to in the second part, we'll try to go through enough examples so you can see that, but realize even if I went through 20 examples with you, once you hit the level of Calculus 1, there's a huge variety in problems, but they all rely on a small handful of concepts. So we'll try to look at examples are the most bang for the buck for what you'll be able to apply in kind of like a plethora of other different looking homework problems. All right, this concludes part 1. We're going to pick up with the rest of it right after this in part 2 with more examples.